Okay, welcome back everyone. It's good to have you back. So it's been a while since we last met. I think it was 2 weeks ago, more than 2 weeks ago. I can't remember, but it's good to have everyone back. And we're going to continue our discussions as well as our materials for the second half of the semester. And so I guess, 2 weeks is a pretty long time to be out of sync with the materials. So please do revisit the materials that we discussed in the first 7 weeks because they're quite fundamental and the materials are going to be useful for the future topics that we're going to discuss at the second half of the semester. So take time to review and then to go back to some of the key concepts. You have the lecture notes. You also have the textbook so that you can navigate from, through the pages. And so please do that. I think that's going to be quite key in, preparing you for the materials in the second half of the semester. So a lot of the things that you learn in the second half of the semester is actually, a continuation of what you've learned in the first half of the semester. So please take time to review it. Okay. I guess the agenda for today is to discuss about heteroskedasticity. This is one of the violation of the multiple linear regression assumptions. And then we're going to also discuss about weighted least square. So weighted least square is actually a form of generalized least square. It's a method to estimate, the parameter of the model given that there is an issue of heteroskedasticity. So we're going to learn about weighted least square as well. I'm also going to provide you with some examples in Stata so that you can do informal graphical analysis to identify heteroskedasticity. And you also be able to do formal tests of heteroskedasticity. And then later on, you'll be able to do weighted least square regression. So that's, I think, the agenda for today. I'm going to start with an overview of the concept regarding heteroskedasticity and the effects of or the consequences of heteroskedasticity in the estimation of our model parameters. Okay, so I'm going to start with just a recollection of the OLS assumptions. Can anyone tell at least the first 5 assumptions of OLS for the multiple linear regression? Anyone?
May I, sir?
Go ahead, Zaki.
All right. So the first assumption is the linearity in parameters. The second assumption is random sampling, if I'm not mistaken. The third is there is no perfect collinearity between the explanatory variables. The fourth assumption is the zero conditional mean assumption, and the fifth is the homoscedasticity assumption.
Okay, thank you, Zaki. Very good. So everyone, that's the first 5 assumptions, the first 5 OLS assumptions for multiple linear regression. First one is linear in parameters. So if you have, estimation with 3 variables, for example, you have beta 0, beta 1, beta 2, and beta 3, and then we assume that all of the parameters are linear. The second is that our data is of a random sample from the population. Okay, so a random sample from the population guarantees that you have a representative sample of the population. If your sample is not randomly selected from the population, then you'll get a biased sample. Okay, and biased sample will eventually lead to biased estimate of the relationship. The third one is no perfect multicollinearity, okay, or no high, high correlation between the variables of interest. And if there is a high correlation between the variable of interest or multicollinearity, then we will, face some issues in the standard error of the estimation. And then the fourth assumption is the zero conditional mean. Okay, I think this is the key assumption of OLS so that we can obtain an unbiased estimate of the parameter in the model. Okay, and then the fifth assumption, which is going to be our focus or center of discussion today, is homoscedasticity. Okay, of course, if you want to go further, there's an additional assumption, which is the normality of the error terms. So the normality of the error terms will guarantee that we're going to be able to conduct hypothesis testing. Okay, so that's going to be the OLS assumptions. So I just want you guys to recall now what are the consequences of those assumptions. Okay, so the first one is that what is the what is the consequences if you fulfill the first assumption, second assumption, third assumption, and then fourth assumption. Okay, so if you fulfill the first four assumptions, then your estimated coefficient will be unbiased theoretically. Okay, so what is unbiasedness? So unbiasedness is an average property in repeated samples. Okay, so if you draw a random sample and then estimate the data, and then theoretically you'll be able to kind of like draw another random sample and then do that multiple times, then the average of the estimated coefficient will actually be equal to the population parameter. Okay. However, again, in practice, we can only draw a random sample, and then given that random sample, we're going to estimate the data. So the assumptions of the zero conditional mean is going to be key here, whether or not the variable of interest is endogenous or is actually exogenous. Okay, so that's going to determine whether or not our estimate is unbiased. Okay. All right, so that's the first four assumptions, and then the unbiasedness theory based on the first four assumptions. If one of the first four assumption is violated, the sample is not random, or the zero conditional mean assumption is violated, then you're going to face with an issue of of a bias estimate of the model. Okay, so that's the first four assumptions, and then the theorem. And the fifth assumption, the assumption that Zaki has correctly given, is the homoscedasticity assumption. So what is homoscedasticity assumption? So homoscedasticity assumption says that actually there is a variance here, but I think it was left out. So the homoscedasticity assumption suggests that the estimated variance of the unobservable conditional on all the explanatory variables is actually a constant. Okay, so that's the definition of homoscedasticity. Today we're going to kind of like focus more on the definition, so that's going to wait for several slides. So what are the consequences of fulfilling the first, second, third, fourth, and fifth assumption? So if you fulfill the first five assumptions, then the square root of this variance is going to be the square, the unbiased estimate of the standard error. Okay. So the standard error is going to be used to conduct hypothesis testing. Okay. So if you remember, if you do a t-test on a particular variable, it's going to be the estimate that we get from the model, which is the beta hat j minus the beta j, and then the standard error of the estimate. Okay, so that's the idea of hypothesis testing. So we need this standard error, and then to ensure that the estimated standard error is unbiased, we need the first four assumptions plus the homoscedasticity assumption. Okay. All right. Any questions so far regarding the assumptions? Okay, very well. Okay, so now I'm just gonna focus on the homoscedasticity assumption, and then we're going to identify what are the challenges and what are the consequences if we relax the homoscedasticity assumption. Okay, so if we relax the homoscedasticity assumption, this means that the data is heteroskedastic. Okay, that's going to be the focus of our discussion. All right, so I'm just going to focus on a simple linear regression model where you regress y on x. Okay, and then given the zero conditional mean assumption, then the estimated value of the dependent variable y is going to be a linear function of x. Okay, so that's the idea. So suppose that this is the x-axis and this is the y-axis, then the expected value of y, which is the regression line, is going to be a function of x. Okay. Now the question is, does the explicative power of the estimated, estimated regression line differs across x? Okay. So I'm going to provide you with, the two scenarios. The first scenario is that the explicative power of the regression line does not vary across x. Okay, so basically the variance of the unobserved factors is constant for all x. Okay, so this is the case. So the explicative power of the regression line is relatively similar for different value of x. Okay, now consider the second scenario. Okay, so the second scenario is the following: you have x on the horizontal line, and then you have y on the vertical line, and say you have a particular regression line. Okay, now for small value of x, okay, so this is just for a supposition, the variance, let me draw a better one, the variance is relatively large. However, for the median value or the mean value of x, the value is actually quite small, the variance is quite small, but then if you go for a large value of x, the variance is also going to get bigger. Now, the second case is an example of heteroskedasticity. The explicative power of the regression line is actually different across x. Okay, so I guess this is kind of like the theoretical definition and probably a theoretical graphical analysis of homoscedasticity and heteroskedasticity. Of course, this is not something that we're actually going to see in the data. We have to do further analysis if we get to the data, but this is kind of like the general idea of homoscedasticity versus heteroskedasticity. Okay, questions, clarification before I move to the next point? Okay, very well. So on the next point, again, the homoscedasticity assumption requires that the error term have the same variance given the value of the explanatory variable. Okay, so for each x, then the variance of the unobservable, the distribution that you just saw in the previous slide is going to be constant. It's constant for all x. Okay. So if we have a multiple linear regression, I guess this is going to be for all dimension of x. Okay, but if we just have y and x, then for all x in the horizontal line, we're going to observe a constant variance of the unobservable variable. Now, excuse me, please note that the assumption is actually quite difficult to fulfill when we get to the data. Okay, so it's going to be quite clear, in a couple of slides or so, that this assumption is actually quite difficult to fulfill. Okay, and so I guess given that I give you guys a heads up that it's going to be quite difficult to fulfill in the data. So this is a graphical analysis where the red line is the fitted value. So basically you run a regression, and then given the regression parameter, you do a fitted line. Okay, and then the dots provides you with the distribution of the actual data that you get. Okay, so the actual distribution of the observations. Okay, now as you can see that there are several values of x where the distribution of the variable is relatively small, but there are some values of x that the distribution is relatively wide. Okay, now this is a very preliminary indication. Again, this is a very preliminary indication that the distribution is homoscedastic or heteroskedastic. This is actually an early indication that this is heteroskedastic, but again, we need to do a formal statistical test to actually conclude that this is heteroskedastic or not. But at least from now, or at least from an informal graphical analysis, we can say that there could be a potential issue of heteroskedasticity. But again, we need to make sure further. Okay, so I'm going to go to Stata, and then in Stata, I'm going to provide you with a simple illustration on how to do the graphing, and then given the graph, what can we conclude from there? Okay, so I'm going to open up the data, and then the data that we're going to use today is going to be the H1 data. So for this exercise, I'm going to provide you with the H1 data, but feel free after the lecture to play around with the other data set and try to identify whether or not there is an issue of heteroskedasticity or not, do informal graphical analysis, and then eventually you can do statistical tests for heteroskedasticity. Okay, so I'm going to do a simple plot. So basically you have a scatter plot of log wage and education, and then you have linear fit and then L wage education. Okay, so this is the plot. Now, this is actually quite similar to the plot that you saw in the lecture note. Okay, I just want to point out that for this particular value of x, okay, so this is for a particular value of x, the distribution of the observation is relatively small. However, if you go to this particular value of x, you can see that the distribution of the observed variable is relatively large. Okay, again, although this is an early indication that there could be heteroskedastic, we cannot conclude that this is an issue of heteroskedasticity until we get into a formal test. Okay, but it's always good to know that there is such test. And so again, from this very preliminary graph, we'll actually learn about another graph after this, but we can use this for early detection of heteroskedasticity. Okay, any questions, clarification before I move back to the lecture note? Go ahead. Okay, excellent. So I'm going to go back to our lecture note, and again, just to provide you with a recap of the homoscedasticity assumption. So we assume that the variance of the unobserved is constant across X, okay? And then given that, it's constant across X, then we can use the estimated standard errors to do hypothesis testing, okay? However, in practice, this is going to be an issue. So when we talked about, for example, the relationship between retirement savings and age, we can see that the variance of the unobservable variable, or at least in the data, we'll see variation of the data across the regression line. Okay. Also in the regression of earnings and then education, we can also say that there could be a potential heteroskedasticity. So I guess the next few questions that we like to identify in this particular lecture is that, one, how can we informally and formally identify the issue of heteroskedasticity? And then the second is, how can we test homoscedasticity, and then the third one is what is the solution. So that's going to be and the key discussions that we're going to have today. So before we go into the detection of heteroskedasticity in the data, I'm going to discuss a little bit about the consequences of heteroskedasticity. Okay. So please recall that in estimation of OLS, there are at least two sets of parameters that we're interested in. Okay. So the first one is we're interested in the estimated coefficient of the explanatory variable. Okay. Suppose that we're interested in the return to education. Suppose we're interested in the return to experience. Suppose we're interested in the relationship between wages and then the hours of work and so on. Okay, so we're interested in the estimated parameter. The second set of parameters that we're interested about is actually the variance of the estimate. Okay, now since we don't observe the population, then we're going to use the sample analog. So the sample analog is the standard error of the beta hat J. So these are the pair that we'd like to identify, okay, given the data that we have. Now, what is the consequence of heteroskedasticity to these estimates? Okay, so basically, heteroskedasticity does not affect the estimated coefficient. Okay, so in this particular case, oh, sorry. So let me go back. So in this particular case, there is no issue in the estimation of the beta hat J. As long as the first four assumptions are fulfilled, then you'll still get an unbiased estimate of beta hat J. Okay. Now, the issue is actually not in the estimation of the beta hat J. If you violate the homoscedasticity assumption, thus heteroskedasticity, you will invalidate variance formula for the OLS estimators. Okay, so that's going to be the issue. So the standard error that you estimate from the data is not going to be valid. Okay, so if the standard error is not going to be valid, the consequence is that the t-test, the f-test are not valid. Okay, so valid here does not mean that you can technically doesn't mean that you technically cannot use it. You can still use it for hypothesis testing, but if your t-test is wrong, your f-test is wrong, then your statistical test is also going to be wrong, and then you may get a trouble. You may get some type of error in the hypothesis testing. Okay, so although under heteroskedasticity, the estimated coefficient is still unbiased, but it's no longer the best. So what does it mean to be the best? Okay. So OLS, given that the assumptions are fulfilled, is actually the best linear unbiased estimator. So the best here means that it has the lowest, the smallest variance. Okay. So it has the smallest variance in the data. Now, if you do not fulfill the homoscedasticity assumption, then OLS no longer provides, it's no longer an estimation that provides the lowest variance. There are other estimation or estimators that could produce smaller or like smaller variance than OLS. So what's the alternative estimator than OLS? We're going to discuss that today. It's going to be referred to as the weighted least square, or the WLS. Okay. All right. So just to recap, the key messages in this particular slide is that you estimate two sets of parameters. The first one is the estimated coefficients. Okay, so even though you violate the homoscedasticity assumption, the estimated coefficient are still going to be unbiased. Okay, given that the first four assumptions are fulfilled. Now, the second one is that we're going to also estimate the standard error of this coefficient. Okay, and that's going to be biased if there is heteroskedasticity. Now, if the estimated standard error is biased, then the t-test, f-test, and then the whole hypothesis testing process is also going to be not valid or invalid. Okay, so that's going to be the issue that we're going to have if there is heteroskedasticity. Okay, so before I go and then move on into detecting heteroskedasticity, let me know if you have questions. Okay, very excellent. So just to recap, our discussions in the previous slide. One, there are OLS assumptions, assumption 1 to 5, and the homoscedasticity assumption, or the fifth assumption, suggests that the variance of the unobservable is constant across X. The homoscedasticity assumption also tells you that the explicative power of the regression line is also constant across different X. Now, in practice, fulfilling the homoscedasticity assumption is going to be quite difficult. It's going to be quite challenging. And so the consequence of violating homoscedasticity is that we're going to get a bias estimate of the standard error, okay, or the variance of the the parameter. Now, if you get a bias estimate of the parameter, then the t-test is also going to be biased, and so our hypothesis testing will not provide the appropriate answer or the appropriate conclusion given the heteroskedasticity. Okay, so given that heteroskedasticity is quite important, and then violation of heteroskedasticity could actually have an effect on the estimate, then it's quite important for us to be able to identify heteroskedasticity. Okay, so just one note up front, you cannot eliminate heteroskedasticity. Okay, it's the feature of the data. Okay, so the idea is that you would like to understand the feature of the data, although it's heteroskedastic. Now, given that you identify that the data is heteroskedastic, you can identify a solution for that. Okay, so you can never kind of like eliminate heteroskedasticity as the feature of the data given the model. Okay, but what you can do is, okay, given that there is heteroskedasticity given this particular model, what will be the solution? That's the way that we should think about it. Okay, because you can never change the data, right? The data is the data, but given the model, the data is heteroskedastic, we'll take it as a feature of the data. Okay. All right. So the first thing that I'm going to do is I'm going to go back to Stata, and then in Stata, I'm going to provide you an illustration on how to do, a simple detection. Again, this is an informal test of heteroskedasticity. Although you'll find that this is heteroskedastic, it doesn't mean that statistically you can reject the null hypothesis that it's homoscedastic. Okay, so we're going to look into that and then see together. Okay, now for this particular example, I'm going to use the smoke data. Okay, so the smoke data provides you with variables that correlate, using all caps lock there. So I'm gonna retype it. So we're going to identify what are variables that correlate with the number of cigarettes smoked per day. Okay, so this is the dependent variable of interest, and then the explanatory variable of interest are going to be the cigarette price, okay, and then income, education, age, the square of age, as well as a dummy variable on whether or not there is a restaurant smoking restriction. Okay, so if that's kind of like a regional, cross-regional features that we can see in the data. Okay, so the first thing that I'm going to do is that suppose that we start with the simplest model possible, that the number of cigarettes consumed per day is a function of the individual income. Okay. Okay, now in this particular case, I'm going to use log income instead of just log income. Okay. All right. So we're right now not interested in the estimated coefficient. Later on, maybe we'll be interested with that. But the thing that we can do is called the RVP plot. Okay. What is an RVP plot? So RVP plot is a feature in Stata that allow you to plot the residual versus the predictor. That's why it's called the residual residual versus the predictor plot. Okay, so I'm gonna use the RVP and I'm going to use the log income as the variable of interest. Okay, and then I'm going to provide just one line, just provide you with a a line that indicates the 0. Okay, all right, so I'm going to run. Can anyone comment on the result of the the residual versus the predictor plot? So this is the residual. Where do we get the residual? We get the residual by subtracting the actual data in the actual data and the projected or the predicted or the forecasted variable given the explanatory variable. Any comment on this finding? Go ahead.
Sir, can I try?
Sure, go ahead, Krishna.
It's maybe the amount of residual is varying in the every level of income, so it shows heteroskedasticity.
Okay, thank you, Krishna. So yes, what we can see is that the distribution of the residual is quite different across level of income. Okay, so as you can see, the distribution of the residual is actually larger for higher income. Okay, again, this is an early indicator of heteroskedasticity. We can't say for sure, or we cannot statistically conclude that this is heteroskedasticity, but this is one of the observations that we can get given the data. Okay, so this is kind of like a very simple test of of heteroskedasticity. All right. Any questions before I move into a formal test of heteroskedasticity? Now, for this formal test, you can actually use a built-in function provided by Stata, and then with just a very simple line of code, you'll be able to get the estimate. I'm gonna go a bit further today. So instead of just using the built-in Stata function, I'm going to show you systematically how we can do the statistical test for detecting heteroskedasticity in the residual. Okay, so that's going to be the agenda. So we're going to go back to the lecture note. Okay, now let's talk about the general testing strategy to identify heteroskedasticity. So there are basically a variety of tests for heteroskedasticity. We're going to focus on 3 of the tests that is available to detect heteroskedasticity. Then we're going to do the example in Stata. Okay. So let the base model be y, a function of explanatory variable x1, x2 until xk. So basically you can have as many as relevant control variables that you can get from the data. Now, after you regress the base model, you're going to calculate the residual, okay? And then we're going to use that residual to identify heteroskedasticity, okay? Now, the first test that we're going to learn is called the Breusch-Pagan test for heteroskedasticity. Okay, so the Breusch-Pagan test simply looks for a relationship between the regressors and the fitted residuals. So the null hypothesis is that the expected variance conditional on different value of x is going to be a constant. Okay, and what's the hypothesis? The alternative hypothesis. The alternative hypothesis is the expected variance conditional on x is not a constant. It could be an increasing function of x. It could be a decreasing function of x. In general, it's not constant. Okay, so that's the alternative hypothesis. So again, just to recap, the hypothesis testing, you have to state the null hypothesis, and the null hypothesis is homoscedasticity, and the alternative hypothesis is heteroskedasticity. Okay. Now let's take a look at the Breusch-Pagan test. What's the strategy? So the idea is that if the estimated residuals, okay, the estimated residuals is the square of the residual, if it's correlated with variables, like a particular variable, or it is correlated with a set of variables, then there is a potential heteroskedasticity. So recall that in the example of residuals on the vertical axis, and then you have log of income in the horizontal axis, you can see that the distribution of the data is actually increasing as you go higher to the higher income. What does it mean? It means that there could be a positive relationship between the residual and the income. If that relationship is significant, it could indicate heteroskedasticity in the data. Okay. Now, how do we statistically test for that? Well, as you recall in the chapter 4, one of the things that we can do is to identify multiple restrictions in the regression. In this case, we're going to test whether or not delta 0, delta 1, delta 2, delta 3 until delta k are simultaneously equal to 0. If they are simultaneously equal to 0, then we cannot reject the null hypothesis. And so we're going to conclude that it's homoscedastic. However, if we reject the null hypothesis, which means that one of the delta k is not equal to 0, then we could have an issue of heteroskedasticity. So I guess that's going to be the idea. So any questions before I move to Stata and then provide you with an illustration of the Breusch-Pagan test? Go ahead. Okay, very good. So in this particular case, what I'm going to do is I'm going to regress just using two variables of interest. The first one is log income, and then the second variable is education or the years of schooling. Of course, age is important. The square of age is important. The log of cigarette price is also an important variable, but for this particular case, I'm just gonna use two variables of interest. You can do that independently after this class, but for this, I'm just gonna use this two variables. Okay, so I'm going to regress the number of cigarettes smoked per day with the log of income as well as the education variable. Okay, so this is going to be my regression, and then after I do my regression, I'm going to request data, okay, to calculate the residual, and I'm going to name the residual as U. Okay, now recall that we're going to regress the square of the residuals on the explanatory variables of interest, and so I'm going to generate U square, which is U to the power of 2. Okay. Oops. Let me increase the size of this. Make sure that you have a good view of the comments. Okay. So what's the next step? The next step is quite straightforward, which is just a regression of the squared residuals on the same set of variable here, which is log income and education. Okay, so that's the regression. Very straightforward. Okay, now what's the null hypothesis? The null hypothesis is homoscedasticity. Okay, technically we're going to identify whether or not we reject or we do not reject delta 1, which is delta log income, and then delta education is simultaneously equal to 0. How do we do that? So it's actually quite easy. We're just going to use these two statistics, the f-test and then the corresponding p-value. Okay. Now, given this p-value, we're going to identify whether or not we're going to reject or we do not reject the null hypothesis. Okay. Now, if you guys recall, since this is the p-value, what can you conclude? Do you reject the null hypothesis or do you not reject the null hypothesis? Given the p-value. Go ahead, Krishna.
I think it can be rejected, sir.
Yeah. Okay, Zaki, assuming what level of significance in this case?
5%.
Yes.
5% level of significance.
Okay, very good. So you can see that the p-value here is lower than the 5% significant level. Okay, so it's not statistically significant at a 1% significance level. However, it's significant at the 5% level, and if it's significant at the 5% significance level, it's also significant at the 10% level. Okay, so if the result shows that we reject the null hypothesis, what's the statistical conclusion? Well, the statistical conclusion, if you reject the null hypothesis, is that heteroskedasticity. Okay, so the Breusch-Pagan test suggests that there is heteroskedasticity in the data. All right, questions, clarifications regarding this? Go ahead.
Sir, just a confirmation so that in testing for heteroskedasticity, we always test that on a joint significance basis, right?
In this particular case, yes.
Also, there are other cases that
Actually, yes. In general, that's the case. You are going to test whether or not the parameters are equal to 0 or joint significant test, right?
Okay, thank you, sir.
Definitely. Okay. Clarification, others? Okay, excellent. So that's the Breusch-Pagan test. I'm going to go back to the slide and discuss the next test. So the next test is called the white test. So the white test takes a very similar approach. It has the same null hypothesis and thus the same alternative hypothesis. It also uses the residual and particularly the squared of the residual. What's different is that the white test adds quadratics. So if you regress with x1 and x2, you're also going to include the squared x1, the squared x2, as well as interaction between x1 and x2. Okay, so unlike the Breusch-Pagan test, where it assumes that the squared residual is or has a linear relationship with the variables of interest, the white test says that, oh, the relationship between the squared residuals and the explanatory variable could be a general relationship. It doesn't have to be linear. It could be a quadratic relationship. It could be a interaction relationship between the variables. Okay. So the white test actually accommodates that the relationship between the squared residuals and the variables of interest could be richer than what the Breusch-Pagan assumed. Okay. So let's go back to Stata, and with Stata, let's identify how we can actually test the homoscedasticity assumption given the white test. Okay. Now, before that, since we're going to regress the squared residuals on x1 and x2, but also on the squared x1 and the squared x2, and then the interaction variable, we need to generate the variables first. So I'm going to generate log income square, which is the square of the log income. I'm going to generate education squared, which is the square of the education. And I'm going to generate an interaction variable between log income and education. And this is just log income multiplied by education. Okay. Right. So we still use the same model. We still use the same residual. Hence, we still use the same squared residual. And now given this, I'm just going to regress U2 on log income and then education, log income square, education square, and then the relation, the interaction between log income and then education. Okay, so it's the same test principle basically. The only thing that differ is that we now include 3 additional variable. Okay. Now suppose that you have 3 variables of interest. So for example, the model consists of log income, education, and then age. Then you need to also include the square of age, the square of log income, and then the square of education, and the interaction between log income, education, log income, and age, as well as education and age. So the more variables that you have in the the estimating equation, then the larger the number of explanatory variables that you need to include in the white test. Okay. So let's run this. Okay. Now, if we run this, then you can see that the p-value is actually quite different with the p-value that we get from the previous regression. Okay. In this particular regression, the p-value is larger than 0.05. It's also even larger than the 0.10 significance level. What does it mean? It means that we do not reject the null hypothesis. Okay. So given the data, we do not reject the null hypothesis. Okay. There is no general relationship between the squared residual as well as the variable of interest. Okay, so you have a conflicting result here. In the Breusch-Pagan test, you reject the null hypothesis of homoscedasticity. Here, you do not reject the null hypothesis of the null hypothesis of homoscedasticity. Okay, so we're going to discuss what should we do in the absence of conflicting test results. But before we go there, I'm going to identify another topic, which is alternative white test. Okay. So I'm going to go back to the slide and let's discuss the alternative white test. Okay. So the issue with the white test is that, there are many regressors. So for example, if you have 2 regressors of log income and education, you need 3 additional variables. Now, if you have 10 explanatory variables, then you need to add the squared variable. So you have 10 plus 10 squared variables, and then plus 45. 45 is the interaction variables generated by the 10 number. Basically, it's going to be 10 combination 2. Okay, so 10 combination 2 and 10 combination 2 is going to be 10 times 9 times 8 factorial, okay, divided by 2 factorial and 8 factorial. Okay, so you can get rid of this. So basically you have 10 multiplied by 9 divided by 2, and so you have 45 interaction variables. So in total, if you have 10 variables, the total is 65 regressors, a lot of variables. Okay, so depending on the size of your data, it could be not appealing, since you have a lot of regressors. And in practice, there are regressions that uses like hundreds, if not thousands, of variable, and so you can easily identify that if you have hundreds or thousands of explanatory variables, then the white test is going to go wild. Okay, so econometricians then identify an additional test, which is called the alternative white test, or the alternative form of the white test. It's a simpler and usually a more effective alternative than the white test. Okay, so the regression indirectly tests the dependence or the relationship between the squared residuals and the explanatory variable. Why the explanatory variable? Because the estimated value of y is actually a function of the explanatory variables. Okay. Similarly, y squared is also the square of the explanatory variables. Okay, and so this particularly simple specification actually captures a general relationship between the squared residuals as well as the explanatory variable. Even though it's very simple, it's actually very rich. Okay, now we just have to test that the delta 1 and the delta 2 is equal to 0 simultaneously or not. Okay, so we're going to go back to stata. However, what's different here is that now we actually have to identify the predicted value of y. Okay, so let's do that. It's not a tall order. So we're going to go back to the previous estimation, which is the regression of the number of cigarettes smoked per day with log income as well as education. Okay. Now, after you do this regression, you're going to ask data to predict the value of the number of cigarettes smoked per day. And let's name that as y hat. And I'm going to generate the square of y hat, which is y hat 2, which is the square of the y hat. Okay. Now, given these variables, and again, we still use the same residual as before, thus the square of residuals, we're going to regress the square of residual u square with the predicted value of y and the predicted the square of the predicted value of y. Okay, and then we run the regression, and again, what we're interested in is the p-value. Okay, so the p-value here suggests that we do not reject the null hypothesis. Okay, so the p-value is larger than 0.10. So in this case, it's 0.2249. So we do not reject the null hypothesis. And so given the data, we can actually identify there is no homoscedasticity. Okay. Sorry, there is no heteroskedasticity, or it's actually homoscedasticity. Now, can we conclude that it's homoscedasticity? The answer is, hold on. We only use two variables of interest. Okay, so recall that we actually have other variables, but we only use log of income and then education as the explanatory variable. Okay, So what we're interested in is actually we need to use more than the variables available, okay? And then what we can do is we're going to test the heteroskedasticity. Now, there are several tests that we can do. The first one is called the the heteroskedasticity test, and then the other one is the white test, okay? So how do we know whether we use this? It's just quite easy. So what we can do is that if you don't remember the command, just open up the help regression and then open up the post estimation regress. Okay. And here you can see that there are several heteroskedasticity tests that you can do. The first one is the ESTAT head test. Okay. If you're interested in the variance inflection factors, so the VIF actually provides you with an information to identify whether or not there is a multicollinearity, okay? But the second one that we're interested in is the information matrix test, okay? And then for the information matrix test, we can actually identify the white heteroskedasticity, the white heteroskedasticity test. Okay, so this is actually very, very straightforward. So we don't have to do all the things that we did in the previous exercise. We can just use the regression result and then do the testing. So I'm going to use cigarettes smoked per day as the dependent variable, and then log of income, and then log of cigarette price. I'm also going to use education, and then age, and then the square of age. I'm also going to use whether or not there is a restaurant smoking restriction. Okay, so basically this is the regression. Oops, let me just do this again. They're very sensitive to the name. Oh, again, making a mistake. There is a sensitive to the name, so it's actually not restaurant, but it's just restaurant. Okay, hopefully I get this one right. Okay. All right, so after we do the regression, okay, what we can do is I'm going to ask data to conduct the heteroskedasticity test. Okay, so again, if you're unsure, you can do the ESTAT heteroskedasticity test. Okay, and then here you can do the heteroskedasticity test. Okay, so there are several options that you like to use, but here this is just the Breusch-Pagan Cook-Weisberg test. Okay, all right. So what I'm going to do is just ESTAT and then HAT. You can use this HATT or you can use the HAT test, whatever you'd like. All right. So again, to identify whether or not we reject the null or we do not reject the null, the easiest thing is to identify the p-value. The p-value here is 0.0000. What does it mean? It means that it is lower than a significant level of 10%, 5%, and 1%. And it rejects the null hypothesis. Okay. So the data suggests that there is heteroskedasticity in the data. Okay. Now, all right, given that there is heteroskedasticity of the data, what should we do? So that's going to be the questions that we're asking, and then after the 5-minute break, we're going to learn about the two solutions that we can do in the presence of heteroskedasticity. All right, so let's take a 5-minute bathroom break as well as water break, and we'll go back at 14:35. All right, I'll see you in a bit. All right. So the next subtopic is heteroskedasticity-robust inference. So this is one of the solutions that we can use in the presence of heteroskedasticity. Okay, so I don't want you guys to focus much on the formula. Stata can provide you with the calculated heteroskedasticity robust standard error, but I just want you to understand the idea behind the heteroskedasticity robust inference. Okay, so again, formulas for OLS standard errors and related statistics have been developed that are robust to heteroskedasticity of unknown form. Okay, one of the important notes for the heteroskedasticity robust inference is that the formula is valid in large sample. Okay, however, since you're dealing with cross-sectional data, you're dealing with pool cross-sectional data, or you're dealing with panel data, then the issue of large sample, wouldn't bother you that much. Okay, but if you're dealing with a very small sample relative to the number of variables in the model, then the heteroskedasticity robust standard error might not be ideal for you. Okay. All right, so the first thing is, let's consider a simple linear regression where you regress y on x. Now, the formula for heteroskedasticity robust OLS is the square root of the following function. Sorry. Okay. So recall that in the absence of squared residual, it's just the normal variance of beta 1 hat. Okay. But for the heteroskedasticity robust inference, you're going to include the squared residuals. Okay. So basically, including the squared residuals here takes into account heteroskedasticity in the data. Okay. So by taking into account heteroskedasticity of the data, your estimated standard error is heteroskedasticity robust. Okay. So here, the idea is that you do not eliminate or remove heteroskedasticity of the data, because you cannot do that. That's the feature of the data given the model. So given heteroskedasticity, you now accommodate it or acknowledge and include that in the estimation of the standard error. So that's the idea of this heteroskedasticity robust OLS standard error. So it's the estimated OLS standard error that takes into account the presence of heteroskedasticity. Okay. Now the idea is the same. So this is a case where you just regress y on x, but there is you're likely to not use that as a regression result, but you're going to use a more general version of regression. Basically, you're going to regress y on x1, x2, x3, and xk. Okay. Now the formula for the heteroskedasticity robust OLS is going to be a bit more complicated. It's going to be a bit more complicated, but we can we can go through it. Okay, so what is R hat square? So basically R hat is the residual from regressing the variable of interest xj on all the independent variables. Okay, now this after that you get the residual and then get the squared residual. Okay, and then you calculate the sum squared of the residual from this regression. Okay, so the sum square is going to be the variation of that variable. Now we use this and with the squared residual to identify the heteroskedasticity robust OLS standard error in the presence of heteroskedasticity. So that's the idea of heteroskedasticity robust inference. Again, we're not modifying anything on the estimated coefficient. The only modification that we do is on the standard error. Okay, so the estimate coefficient will be the same with or without the robust standard error, but the estimated standard error is going to be different with this heteroskedasticity robust method. Okay, we're definitely going to check that in the stata, but before that, we need again to note that by using the formula, the t-test is valid asymptotically. So what does it mean for a t-test to be valid asymptotically? It's valid given large sample, okay? So now we can use this estimator into the denominator of a standard t statistic. So instead of calculating t equals to beta hat j minus beta j divided by the standard error of beta hat j, now the denominator, the standard error of beta hat j, you can use the heteroskedasticity-robust version, okay? Now, the t-test version, the f-test version of the heteroskedasticity-robust is available in most statistical software, and particularly in Stata. So we're going to see that, okay? So again, while the robust standard errors are consistent for any kind of heteroskedasticity, so this is the good thing about the test, is that it's consistent for any kind of heteroskedasticity. The test or the estimation rely on asymptotic approximation. So you need a relatively large sample and maybe bias in relatively finite samples. Okay, so I'm gonna start first. Before I continue, please let me know if you have any questions. Okay. All right. Very well. So I'm going to continue in Stata. The application in Stata is very, very simple. What you need to do is that you just add an option, which is called the robust option. Okay. And then using this robust option, you can get heteroskedasticity robust standard error in your regression. Okay. All right. So let's continue to Stata. Okay. All right, so the first thing that we're going to do is we're going to run the same regression that we ran previously. So here I'm going to use regress the number of cigarettes and then lock of income, lock of cigarette price, education, age, the square of age, and then whether or not there is a restaurant smoking restriction, okay? So what I'm going to do is just add the robust option. You know, if you're pretty lazy as I am, then you just have to add the R option, okay? Which is going to be the abbreviation of the robust, okay? But since this is our first try, I'm just going to use the robust version. Now, pay attention to the following. In particular, pay attention to the estimated coefficient and the estimated standard error given the heteroskedasticity robust option. Okay, let's just take one variable, which is the log of income, and then run. Okay, so previously the estimated coefficient is 0.8802. With the estimated robust standard error, it doesn't change. Okay, again, heteroskedasticity robust standard error only affects your estimated standard error. It doesn't affect your estimated coefficient. But as you can see here, the estimated standard error without the heteroskedasticity robust version was 0.72. With the addition of heteroskedasticity robust option, it's now lower at 0.59. Okay. And so the other estimated robust standard error are actually now different with the option without the standard error. So what's interesting is that for the log of income, the heteroskedasticity robust standard error is actually lower. However, for the log of cigarette price, the estimated standard error is actually now higher. Okay. The big question is, what causes the fact that one is underestimated and the other one is overestimated. It really depends on the relationship between the variable of interest and then the other explanatory variables in the model. Okay, and that's going to affect the estimated variance of the variable. Okay, so now given that we use the heteroskedasticity robust standard error, then the t-tests are valid. Okay, the f-tests are actually also valid, the confidence interval as well, now since you have the estimated standard error and the p-value. And so given the heteroskedasticity robust standard error, you now can actually do inference. Okay, all right, so that's the idea of heteroskedasticity robust standard error. So it's very simple, it's very straightforward, and basically there's almost no penalty of using heteroskedasticity robust standard error as long as you have a relatively large sample. Okay, so even if you do not statistically detect heteroskedasticity, you can still use heteroskedasticity robust option, as there is no penalty in terms of efficiency or in terms of the estimation of the coefficient, since it doesn't by theory affect the estimated coefficient. Okay, so that's the idea of heteroskedasticity robust standard error, which is one of the solutions that you can do. Now later on, as you go on and explore a more complex model and a more complex estimation design, then your heteroskedasticity robust method could be different. Okay, so in the future, I'm going to introduce what's called the cluster robust heteroskedasticity standard error. In the case that there is a cluster design, or for example, there is a relationship in the factors that we do not observe within a particular unit. This is quite common if you have a panel data, for example. Now, if you have a panel data, then it's ideal to actually use the cluster robust standard error. Otherwise, the estimated coefficient, the estimated standard error will be lower than the actual. So it's going to be underestimation, which is actually not good, since you're going to commit to what's called the type 1 error. Okay, so the probability of rejecting the true null hypothesis is going to increase in the case of cluster correlation in panel data. But it's for panel data for now. Let's focus on the cross-section data first. Any questions on robust heteroskedasticity robust standard error? Let me know.
Sir,
Yes, go ahead, Matthew.
is there like a rule of thumb to determine how large the sample size should be if you want to use heteroskedastic robust standard errors?
Unfortunately, I don't think so. It really depends on the number of variables as well. So, you can have, say, you can have 60 observations, but you have like, say, 30 variables of interest. That's also going to play a factor on the estimated heteroskedasticity robust standard error as well. But I guess like it's not a rule of thumb, but in my general experience using cross-sectional data, pooled cross-sectional data, using panel data, particularly from microdata, you won't get into this trouble. Okay, so I cannot say what's the number, because it's going to be different from one case to the other. It really depends on the degrees of freedom as well and the number of variables. So it's quite difficult to know. Okay, but in general, as you have more and more, theoretically, if you have more and more observations or more sample, then you're going to get the proper estimate of the heteroskedasticity robust standard error. Okay, and so I mean, at the end of the day, you're going to use the data that you get, but if you suspect that your sample is relatively small, then you have to note that there could be an issue with the estimation of the heteroskedasticity robust standard error, as it is valid asymptotically, or it's valid as the number of sample increases. Okay. Any other questions or clarification? Go ahead. Okay, great. So let's go back to the let's go back to the slide, and we're going to learn about the weighted least square. Okay. So recall earlier that if you use OLS and there's a presence of heteroskedasticity, then OLS is no longer the best linear unbiased estimator. It's no longer the best because it doesn't produce the smallest variance of all other class of estimators. Okay. Now there is actually a more efficient estimator. A more efficient estimator means that it's an estimator that produces lower variance in the presence of heteroskedasticity. Okay, and this estimator is referred to as the weighted least square, and it's an alternative to OLS. Okay, the weighted least square estimator is also known as the generalized least square estimator, or the GLS. So the key feature of this WLS is that we need to know the correct functional form of the variance of the unobservable. Again, this is very challenging in real world application. Why? Because we need to check the relationship, and then given the data, we need to make assumption to say that, hey, this is the correct functional form. We're of course going to do that in Stata, but before we go into that, exercise, I'm just going to go through some of the details about weighted least square. Okay. So we try to estimate the model which contains heteroskedastic errors. Okay. So we're going to assume a specific form of heteroskedasticity. Okay. So in particular, the variance is going to be variable, so it's gonna change, or it's gonna vary, and it's gonna vary by explanatory variable x and some function h. Okay, so the function of explanatory variables determines the heteroskedasticity. Okay, so the key here is that there is this function h of x that determines the heteroskedasticity. Okay. So, I mean, for the sake of discussion, I'm going to assume that the function is known. In practice, though, you wouldn't know what the function is. It could be some linear function. It could be some nonlinear function. How do we actually determine which function is the best? That's an empirical question. That's an empirical exercise that we're going to go through together. Okay, but let's now assume that we know the function. So the goal of WLS is to transform the error into an equation that has homoscedastic error. So by theory, if you assume the following h function and do a modification or a transformation of the error, given that function, then we're going to get a estimation that satisfy the Gauss-Markov assumptions. Okay, particularly the homoscedasticity assumption. So the other assumption still needs to be challenged, particularly the zero conditional mean assumption. However, given the transformation, you can fulfill the fifth homoscedasticity assumption. Okay, all right. So since h is just a function of x, okay, so again, it's just a linear function of x. What we're going to do is we're going to transform the error term by dividing it with a square root of h. Okay, it might not be clear why we divide this with a square root of h, but it will in a in the end of this slide and the couple of slides. Okay. So basically, since take a look at the variance of the factors that we do not observe is actually sigma square h. Okay. Now, if we transform the error term by dividing it with the square of h, then if you take a square of this one, it's going to be expected error square divided by hi. Now, again, what's the estimated u square? The estimated u square is actually equal to the variance, and then it's assumed to be sigma square h. Okay, so sigma square h divided by h. It's sigma square. So by transforming the error term with the inverse of square root of h, then theoretically we can get homoscedastic assumption, homoscedastic value. Okay. So since we divide the error term with 1 over square root of h, we have to do that for all variables in the model. And so basically the transformation is 1 over square root of h. Okay. So that's the transformation in the data. And then y star is the transform y. X1 star is the transform x1, which is x1 divided by the square root of h. Okay. Now, again, why do we want to make this transformation? We make this transformation such that we obtain homoscedastic error. Okay. Okay. Now, one example is the following. Suppose that you have savings and income, and then you assume that, again, you assume that the heteroskedasticity is driven by the income variable, and it's actually driven linearly. So what you need to do is you're going to transform the equation by dividing it with the square root of income. Okay, so you're going to regress it with the transform saving and the transform income. Notice that the transformation doesn't have any effect on the estimated beta 1 as well as the estimated beta 0. So your interpretation is going to be similar. Your interpretation is that if the income variable increases by a single unit, then savings will going to increase by beta 1 unit. So it doesn't change the interpretation, it just changes the estimation strategy. Okay. All right. So the idea of the regression is quite similar. You're going to do OLS on the weighted least square. Okay. And basically, the idea is the following. So observations with large variance will get a smaller weight. Okay. And then observations with a smaller variance is going to get a larger weight. Okay. The big question is, why is WLS more efficient than OLS in the original model? Because it provides different observation with different weight depending on how large is the variance. Okay. If the variance is large, it's less informative, and so you give it less weight or a lower weight. But you have a small variance, the information is quite valuable for the estimation, and so you should give it a larger weight. So that's the idea on why the WLS is more efficient, because you basically give lower weight to the larger variance. Okay, observations with the larger variance. So that's the idea of the WLS and why it produces a lower variance than the standard OLS. Okay. Now, in the previous discussion, okay, before I go there, actually, let me know if you have questions before I move on. Go ahead.
Sir, I have a question.
Yeah, go ahead, Alexander.
So how should a researcher determine the weighting in the weighted list squares? Is there any rule of thumb in that?
Yeah. Unfortunately, there is no rule of thumb. So as mentioned in a previous slide, it's actually very challenging to identify it. So it's actually an empirical exercise. We're actually going to do it. So we're going to identify, different relationship between the squared residuals as well as the variables of interest. Okay. But yeah, there's no rule of thumb. So it's really is an empirical exercise. Okay. Any other clarification, questions? Okay, awesome. So now when the functional form of heteroskedasticity is unknown, we're going to model the functional form. Okay, so let's assume that the h function is an exponential function of x1, x2, x3, and so on until xk. Okay. So under the assumption that the heteroskedasticity is driven by some form of this exponential function, okay, then if we take a log of the squared residual, then we assume that the error v is actually independent of x. So we're going to get the following regression. Where do you get this particular regression? You just take a log transform of this one. Okay. All right. So let's go one by one. A log transform of sigma square is going to be a constant. A log transform of the exponential is going to be whatever is inside this function. Okay. So that's the idea of the transformation. So basically, this is the idea of the GLS procedure. Of course, you're not going to go this, line by line. We're going to use a, built-in function in Stata that will actually allow you to obtain the estimation right away. But here's the idea. So you run the regression of y, x1, x2 until xk, calculate the residual, take the square of the residual. Okay. And then after you take the residual, calculate the square residual, take the log transformation. Okay. And run the regression in equation 2 and obtain the fitted values g hat. Okay. Now we're going to exponentiate the fitted value g hat, and then we're going to get h hat. And this h hat, or the inverse of the h hat, is going to be the weights for the weighted least square. Okay. And so basically you just have to divide the left hand side with h hat, and then the right hand side as h hat. Again, the transformation only affects the variable. It doesn't affect the interpretation of the estimated parameter beta 1, beta 2 until beta k. Okay. All right, so I'm going to go back to Stata, and then I'm going to provide you with an illustration of the exercise in Stata. Okay, so the first thing that I'm going to do is that I'm going to run a regression. Okay, so I'm going to run a regression. Basically, this is the regression that we did before. This is a particular exercise. There are like tens of data from Jeffrey Wooldridge textbook out there. So feel free to just randomly choose one data, and then as long as it's a cross-sectional setup, and then given that, do your independent exercise and then follow all the discussions that we had in this lecture. I think that's going to provide you with that intuition further on what is heteroskedasticity, how do we identify heteroskedasticity, and so on. All right, so I'm going to run the regression. So the first thing that I'm going to do is I'm going to do an RVP plot on each of the regressor. Okay, so I'm going to do it for the income. Okay, and then I'm just going to add a y line which is equal to 0 to identify the zero line. Okay, so this is what I get for the log of income, And then I'm going to do that for all the variables in the regression model. Okay, so I'm going to do that for the log of cigarette price, okay, which has this particular relationship. So as you can see, there is relatively large distribution on the larger cigarette price. Okay, and we can also do this for the education. Okay, so for the education, it seems that there is relatively similar variance. Again, with this eyeball test, we cannot say for certain whether or not it's statistically significant or not, but it's an indication nevertheless. Okay, so I'm going to ask the Stata to run this one by one. So Stata is going to provide you with this summary of, okay, these are the variables used. You have log of income, cigarette price, years of schooling, years of education, age square. Actually, okay, let me so this is going to be the variables that you get from the regression. Okay, so this will provide you with an intuition. It could be that, okay, the log of income and then the log of cigarette price can be something that we need to include in the regression. Maybe also with the age, because we can see that there is a potential age in the regression. Okay, but we'll do that one by one. Okay, so the first thing that I'm going to do is I'm going to do a WLS 0, and then cigarettes, and then log of income, and then log of cigarette price, and then education, age, square, restaurant, and then the weighting variable that I'm going to use is log income. I'm going to start here first and then build up from there. And then what I'm going to do is just the absolute error, and I'm going to also use a graph for this one. Okay, now, oh my god, my bad, it's actually a restaurant, but restaurant. Okay, so if you run the regression, and then this is the what do you call it, this is the weighted residual. As you can see, the residual doesn't seem to be homoscedastic. Okay, you can see that there are some points where the distribution is relatively narrow, but there is some portion that the distribution is relatively wide. Okay, so maybe we should explore more about the data. Okay, so I'm going to try again. Okay, so instead of just using, so instead of just using log income, I'm going to use L cigarette price. You can also use education, age, square, as your weighting variable. Okay, and then you do that, and then you're gonna get this following. Okay, now just be very careful. It seems that, oh, it's very neat. Okay, but the issue is that it could be driven by this this large variable here. So you have to be very, very mindful that although it seems neat, variance is very tidy, but it could be just a scaling issue of the graph because of this one. Okay, but before I go there, I'm just gonna do another example. Okay, so I'll just take one more example. And then instead of using the absolute error, I'm going to use the log of e square. Okay, so basically this is, the one that you actually use in the previous example. Okay, so we're gonna run the regression, and then, wow, okay, doesn't seem there is no scaling issue here. Yes, there is definitely some outliers here, here, and here, but it doesn't change. It looks like there is no scaling issue. There could be, but it's quite difficult to tell from this one. But I think there is indication that this could work a bit better than the previous specification. Okay. So I'm going to try one more and then see where that leads us actually. So I'm going to use the WLS and then instead of using log E, I'm just going to use the squared residual. Okay. And then I'm going to run the data again. Again, this could be a scaling issue. So we have to be very careful in trying to identify which of this weighting is actually, better. All right, so we've seen several methods, that we can use to identify the weighting variables, and then some of the results provide us with a different estimated coefficient, a different standard error, which is rightly so, given the transformation. But as you can see here, the estimated coefficient and standard error are going to be different from one estimation to the other estimation. Okay, so please be mindful when we're using the estimation. You could get a very, very different result. And then if you compare it with the initial one, it's going to be quite different as well. So be mindful that that could be that result. Now, which one should we actually choose as the main, estimation of interest? The answer is that it's quite difficult to tell right now. Again, we need to look at the study and then how this study was, conducted to actually know which one was the most optimal. But given that we have a lot of variables, what we need to do is that we systematically use with one variable, and then given that one variable and then a particular type of weighting method, look at the graphical analysis, and then use a different sets of variable and then look at the graphical analysis. And we have to use that over and over again until we find the optimal one. Okay. Now, the big question is, which one is going to provide you with the best? It really depends on the distribution of the weighted residual with respect to the fitted value. And one thing that you need to note is that the graph could be sensitive to outliers. So if you have an outlier, it could seem that, oh, it's compressed and then it looks like a homoscedasticity, but you have to be very careful in interpreting that regression. Okay, so be mindful of that step, and with that process, in Stata. All right. Any questions, clarification to the point here? Go ahead. Okay. Please, if you have any clarification. Okay, so basically now, given the weighted result, we can see that the estimated coefficient provides you with the estimated effect of these variables. Okay, so I'm going to go back to the initial regression, and then from the initial regression, you'll see that log of income and log of cigarette price does not have any significant effect on the amount of cigarettes consumed per day. Okay, which is quite weird because we could think that, well, income is going to be important, And then we can think that, oh, log of cigarette price is actually also going to be very important as well. Okay, so after we do the weighted least square, now we get still a positive relationship, but now it's statistically significant. Okay, and then we also get the log of cigarette price, and then we can also find that there is a negative relationship. Okay, so this is actually quite interesting result that is it's quite consistent with the theory that as prices of cigarettes goes up, your demand for cigarettes goes down. Okay, the more educated you are, probably you're more aware of the risk, and probably you have a relatively healthier lifestyle. You're more likely to smoke as well, and then the assumption, the demand for smoking is lower. Okay, so it's interesting that, you know, as you age, you consume more cigarettes, but the additional cigarettes that you consume decreases every year. Okay, because there's a nonlinear relationship between age, between the cigarette smoke, and then H square. Okay, all right. Let me know if you have questions regarding the estimation of WLS. Again, it's a function of going through every variable in the data set and then try to do a diagnostic review of the relationship. And then from there, you can identify which one is the most optimal. Okay, go ahead.
Sir.
Yes, go ahead, Alex.
So understanding that there is a change of significance in the variables of income and cigarette price effect on the number of cigarettes consumed, as you mentioned before, when we are comparing with the use of OLS and WLS. Does that mean that in practice OLS is no longer sufficient for estimating the parameters and the significance of each variables?
Yeah, in the presence of heteroskedasticity, OLS is relatively inferior to weighted least square. Okay, so yes, if there is an issue of heteroskedasticity, you should use the weighted least square instead. Okay.
Sir,
Yes, go ahead.
I wanted to ask about the static WLS regression.
Mhm.
For the type you use the squared residuals and the log of squared residuals. What's the difference between those two, and which one should we use? Yep, that one.
Okay. So this is just a different way of the weighting method. So I'm just going to go back to the slide. Wait, hang on. Let me find my slide. Okay, so it's actually just a different way of looking at the slide, looking at the function. So recall that here we assume that the heteroskedasticity is caused by this exponential function. Okay, and so given this exponential function, we're going to do a log transformation, and then given a log transformation, we're going to estimate delta 0, delta 1, delta 2, and then delta k, and then use that as a weighting for the model. So it really points out to which of the weighting function that we're going to use. Okay, and so basically, which one is the best? The answer is difficult to say. It really is going to be a function of looking at the performance of each variable in terms of whether or not there is that heteroskedasticity in the data. Okay, so it's quite difficult to say. And then from one variable to the other variable, it's just going to be quite, quite difficult to do. Okay. Now, the next question is, shall we use a robust standard error when we use the weighted least square? The answer is yes. It's you can use the weighted. You can still use the robust function when you use the WLS. It's gonna provide you with heteroskedasticity-robust standard error. Okay. Now, so I guess that's going to be a lecture on heteroskedasticity. Any last question before I conclude today's section? Okay, excellent. As always, I'm going to upload the video on YouTube for your future reference, and I'm going to include the link on your ELOC. I'll see you guys next week. However, since next week is already Ramadan, then we're going to have a blended learning session. So we're not going to have a full 2 meetings, 2.5 hour meeting in the course. So I'm going to provide you with the video that you can access several days before the lecture. And so the lecture is just going to be a confirmation of any questions that you have, any clarifications that you have. And so it's just going to take a relatively short period. So it's probably 45 minutes. If you don't have any questions, then the session is going to get shorter as well. Okay. So I'm going to provide you with a description on the way that we conduct the course via email. For the meantime, I'd like to, say my best for those who observe the month of Ramadan. Best of luck. It's a challenging time during the pandemic as well as these online courses, but hopefully with the relatively setting at home, it's gonna make the Ramadan a bit easier for everyone. So thank you so much. I'll see you guys virtually next week as well, and wait for my email for further instructions. I'll see you guys. Bye-bye. Have a good rest of the day.
Thank you, sir.
Thank you, sir.